My name is Natalya Kramarova. I'm from NASA Goddard Space Flight Center, and I am PI for ozone products that we derive from multiple OMPS sensors, not just from LIMP, but from nadir as well. But today I will talk mostly about LIMP Profiler, and LIMP Profiler is LIMP scattering instrument, and I will talk about our decadal experience working with SOMI and PP LIMP Profiler, what we learned, and hopefully I will summarize it in my talk. I would like to acknowledge my colleagues. Most of them are from NASA Goddard Space Flight Center. We also have collaborators from University of Bremen and from NOAA Boulder, who helps us with validation. It's nice that I don't have to introduce what is LIMP scattering technique here at this meeting, but I will just say a couple words that LIMP Profiler is a part of ozone mapping and profiler suite, and we have 3 sensors on SOMI and PP. Nadir Profiler, which measures between 250 nanometers and 310 nanometers and look directly at nadir, and we can retrieve ozone profiles with coarse vertical resolution from that instrument to continuous BUV record. We also have Nadir Mapper, and Nadir Mapper has very wide swath, and it provides global maps of total ozone daily. First SOMI and PP OMS was launched in October 2011, and operational measurements started approximately in April 2012, and by now we have more than 10 years of observations. The second OMPS was launched in November 2017, but unfortunately it had only 2 nadir But unfortunately, it had only 2 nadir sensors. It didn't have LIMP sensor. And last fall, we have another addition to our OMPS family. We have 3 other sensors on Node 21, including LIMP Profiler. So total, we have 8 sensors, 8 operational sensors, and we kind of take care of all of them. So what kind of products we can derive from LIMP Profiler? And this is a list of products that we kind of derive at this moment. The first product is obviously measured LIMP scattered radiances. We deliver level 1 G product, which is available for everyone, and other groups use this product to run their own level 2 algorithms. Then we have ozone profile product, where we use UV and visible wavelengths to produce vertical ozone profile between 12 and 57 kilometers. Then we have aerosol extinction product, which Hassan is PI for, and it uses visible and near-infrared wavelengths to derive aerosol extinctions at 6 different wavelengths. Then we have cloud height product. This is just a simple ratio between the 2 wavelengths that allows us to discriminate between aerosol and cloud tops. That's important for ozone retrievals because we don't do ozone retrievals below the cloud top. So we stop our algorithm at the cloud height. And then we have several research products. Probably you saw a poster on Tuesday by Tsong Chen about upper stratospheric and mesospheric temperature profiles. Then we have mesospheric ozone product, which is also a research product, and stratospheric NO2. You heard one presentation yesterday by Jinping Mok, and Michael Hims will talk a little bit about that today as well. So why do we need LIMP scattering observations? What is good about LIMP scattering technique is that it's relatively inexpensive technique, but it allows you to measure ozone globally with relatively high spatially dense sampling and very high vertical resolution. And why do we need these observations? For many years, we have total ozone records, and we can look at the size of the ozone hole. And that is one of the metrics of the health of our Earth layer. And here I would like to kind of focus on 2 years. I don't know if you see my mouse. Okay. 1 year is 2019 and the other year is 2020. That was 2 very different years. In 2019, wave activity was very strong and the vortex was disrupted early in mid-August. And as a result, we have relatively small ozone hole, which was the smallest from beginning of 90s. And if you look at vertical ozone distribution, you can see that in the lower stratosphere, the layer between about 12 to 20 kilometers, that's the layer where always photochemical ozone depletion happens. You can see that there still was depletion. Ozone dropped from about 12 DU per kilometer to about 8 DU per kilometer from beginning of September up to the beginning of October. But because the vortex was so weak and we had a lot of meridional transport, you can see that higher ozone values were brought from mid-latitudes to the polar latitudes, and finally they were pushed down by downward motion, and the ozone hole closed very early in 2020. Oh, I'm sorry, in 2019. In 2020, situation was completely different. The wave activity was very, very weak, and the vortex was strong. Temperatures were consistently below average, and as a result, we had very large ozone hole, very deep and large ozone hole. And if you look at the distribution, vertical distribution of ozone, you can see how ozone was dropping from about 12 DU per kilometer to less than 1 DU per kilometer at the early October. But at the same time, you can see that ozone depletion ceased by about like first week of October. After that, ozone did not drop anymore. Why ozone hole stayed there? It stayed there because of dynamics. The vortex was very strong and it prevented meridional transport. We didn't have any kind of inflow of high ozone from mid-latitudes, and that's why the vortex stayed so long, almost by the end of December. For instance, some ground-based stations over Antarctica measured UV index up to 12. And for comparisons, 12 is a typical UV index for tropical latitudes. So it's very unusual and very high UV index. So if we look at, and since then we had 2 other ozone holes, 2 other seasons, which were very similar to 2020. In 2021 and 2022, ozone circulation was, atmospheric circulation, stratospheric circulation was very similar to 2020. We had a strong polar vortex, we had low temperatures, and as a result, we had large ozone holes. So if we look at ozone hole area in September as a function of time, you can see that these 3 years kind of represent relatively large ozone hole area. But then if you subtract ESC feet, which is shown here as a gray line, you will see this scatter of points. And these points are very highly correlated with the temperature, with the temperature at 50 millibar in September over Antarctic. And you can see that the last 3 years were very close to that temperature feed. So the point that I'm trying to make here is that there were a lot of speculations about the role of aerosol, for instance, from Australian fires, or from La Sulfur volcanic eruptions or Honga Tonga eruptions, and if they play any role in Antarctic depletion. These results suggest that even if they play some role, that role wasn't major. The major contribution came from very unusual dynamical conditions that we have in the last 3 years. So this is another example Matt DeLand published this paper in 2020. As I said, we can determine the cloud top. But if we have additional information, like for example, temperature from BIRA-2, we can classify these clouds and we can determine if it's a polar stratospheric cloud or not. And we can measure a frequency of polar stratospheric clouds. Over Arctic in winter 2019-2020, we had very unusual conditions. The winter, the stratospheric temperature were very low, and as a result, that produced a lot of polar stratospheric clouds. This is actually in LP record, this is the year with the largest frequency of polar stratospheric clouds over Arctic. And you can see that many of them were observed in March and April. And this is a time where we have a lot of UV light over polar latitudes, and that facilitates photochemical ozone depletion. As a result, we saw this depletion in our LP record, and you can see that between 12 and 20 kilometers, ozone was almost 30 by 50% lower than climatological means. And these results correlate very well with MLS measurements and with total ozone observations as well. So why, what is the other reason? Why do we need ozone observations? Ozone is a trace gas, and we can look, for example, at these ozone anomalies plots over tropics, and they sort of change with a QBO, and this is like a nice figures that shows us how QBO propagates in equatorial stratosphere. And on the top is a plot from OMS LP, and on the bottom from MLS. And you can see, for example, disrupted QBO in 2016, 2017. So this is another example why we need limb scattering observations just to monitor large-scale circulation. Another benefit of limb observations is a vertical resolution. With such a vertical resolution, we can resolve features in seasonal ozone variations. For instance, at high altitudes, above 50 kilometers, ozone seasonal cycle is highly anti-correlated with the temperature seasonal cycle. And you can see that it's shifted, the seasonal cycle at above 50 kilometers is shifted from the seasonal cycle that we see in total ozone or in low stratospheric ozone. There is also kind of transition area where the seasonal variability in ozone are relatively small. And limb observation allows us to reconstruct these features that are very hard to get from nature observations. This type of analysis is very useful, for example, for model validations or for instance for assimilation. So Chris did experiment where they assimilated OMS LP observations in BIRA-2 system and compared these assimilations with the standard assimilations where they assimilate MLS. And overall, they found very good agreement between MLS and OMS LP assimilation experiments, and also very good agreement of two experiments with sound measurements, which are shown on this plot. But this study indicated that the drift that we had in previous version of OMS kind of complicates assimilation process, and it's very hard to remove trend from observational record. And for the last 3 years, we spent a lot of time looking at altitude registration. So there are two types of errors that are dominated in limb scattering technique. The first one is altitude registration, and the second is radiometric errors. But I will focus on altitude registration here, and why do we need altitude registration? So the instrument is looking through the atmosphere in the limb direction, and we need to know exactly where it pointed, where the instrument is pointing, to know where the location of this tangent point. And small deviations in pointing can create relatively large errors in retrieved ozone. So the plot here shows the errors, estimated errors in ozone retrievals due to small changes in altitude registration. So if you have error about like 200 meters in altitude registration, that will create errors of order of 5% at altitudes above 30 kilometers, and they relatively stable as a function of altitude. And then you will have switch of sign around the peak, the ozone peak, and then the sign of these errors will be negative below the peak. And this is a typical pattern for the errors in altitude registration. So OMI and PP has 2 star trackers, but very early at the beginning of the mission, we found significant offset between the information that were coming from star tracker systems and our own observations. And that forced us to develop 2 techniques to sort of validate our altitude registration. One technique is called AirSAS. It's relay scattering altitude sensing technique. What it does, it looks at the profile shape of radiances at 350 nanometers. This is a wavelength which is not sensitive to ozone absorption, and it changes as a function of air density. For this technique, we look at the ratio between 40 and 20 kilometers, and that ratio is very sensitive to small offset in altitude registration. However, this technique is very sensitive to aerosol. So for instance, you don't have any aerosol typically at 40 kilometers, but you might have a lot of aerosol at 20 kilometers. And that limits application of this technique to areas where you have very low aerosol or time periods where you have low aerosol. And then we also use another technique, which we call absolute radiance residuals method. And that method uses short wavelengths at very high altitudes, where these wavelengths are not affected by ozone. I mean, there is still sensitivity to ozone, but it's very, very small. Those radiances increase very rapidly as a function of altitude. It's about like 10% gradient over 1 kilometer. So 100 meter error in altitude will result in 1% error in this method. So this method is very sensitive to changes in altitude. And the sort of shortcoming of this method is that it's very sensitive to absolute calibrations. We use combination of these 2 methods to apply altitude corrections. In version 2.5, as well as in our recent version 2.6, we have 3 types of corrections. The first correction is absolute correction. We apply this just constant number for all 3 slits. They're slightly different for the 3 slits, but the number here is for the center slit. So we apply this as absolute correction, and then we have intraorbital correction. The intraorbital correction in version 2.5 was based on ARM results, and it had intraorbital dependence, but also seasonal component to that. In this version, we simplify this correction. It's just simple linear feed. It's about 650 meters from one end of the orbit to another. And it's also based on ARM results. And then time dependent. And time dependent is the most complicated. In previous version, we adjusted for 2 steps. The one step was on April 2013, and we sort of have confirmation from Star Tracker team. That kind of coincide with the time when they switched from, they first used only one Star Tracker to resolved satellite position, but then they started using 2 of them, and there was like 100-meter offset that they didn't account for. So that's a step we saw in all our measurements. But then in version 2.5, we erroneously apply another correction in September 2014. And if you look at these two lines, the red line is AirSAS time series in Southern Hemisphere from version 2.5, and the blue line is from the recent version 2.6. So in version 2.6, we removed that correction in September, and you can see sort of like a drop here. But at the same time, if you look at long-term record from the blue line, it's way more stable than the red line. And the red line had like about 100-meter drift, even more than 100. It's like about 150-meter drift over this time period. But you also can notice differences in sort of interannual variability between the two records. Some of them related with change in with other changes that we implemented in version 2.6. Aerosol correction, also simplification of intraorbital correction, where we removed seasonal component from that. We also updated ozone and NO2 cross sections. All of these, it's very small changes, but all of them kind of affected these AirSAS results. So now we kind of believe that we don't have any substantial drift in version 2.6. And here's a plot with relative drift between version 2.5 of OMS Limb Profiler and MLS. And you can see this feature where the drift is mostly positive above ozone peak, and it's mostly negative below. And it's even better seen here on these plots on the bottom. And this pattern is consistent with a possible drift in altitude registration. So this is what we have in version 2.6. And you can see that these features mostly go away. If we look at the patterns, we don't see any clear patterns. So there might be some remaining drift, at least we see it with respect to MLS, but it's definitely not related to altitude registration anymore. So you will ask a question, okay, what will happen when MLS will go away? How will we validate our altitude registration? And that's why we decided to start looking at our own OMS nadir profiler measurements. And the plot here shows you original time series. There are 3 lines here. The red line is MLS. You don't see it. It's kind of on the bottom. And then blue and yellow ones represent, so blue represents LP, and yellow represents nadir profiler. And then we subtracted MLS from both of them, from LP and nadir profiler. And on the bottom, you can see like when you remove all seasonal biases, that's what you will see. This is kind of remaining anomalies. And the fact that the differences between OMS LP and MLS and OMS LP and nadir profiler are very similar, it means that whatever features we see here are coming from limb profiler. And if you look at this time series, there is no obvious drift, but there are rather some kind of steps. So if you look at first 3 years, it looks like relatively flat. Then there is something kind of going from 2014 to 2018. Then there is like small drop, and then again it's flat. But there is no obvious drift in LP record. Another method that we consider as a validation tool for altitude registration is comparing reflectivity between nadir and limb. So we derive reflectivity from limb observations at 40 kilometers, and we also derive reflectivity from nadir measurements. And we, for these purposes, we compare only over Pacific, where we have relatively homogeneous underlying scenes. And the two records show that there is no substantial differences in the time record in terms of stability. But again, this method also has a lot of uncertainty. So if you look at these shaded areas, it's just like daily measurements. And then when we smooth them and run kind of like long-term smooth, that's the solid lines that we see here. In addition to changes in altitude registration that are very important, we did several changes in the algorithm. And I want to talk a little bit more about like stray light correction, which seems to help with visible observations. But then like in level 2, we updated ozone and NO2 climatologies and cross sections. They didn't have much effect on ozone retrievals, but the largest changes were that we now combine UV and visible measurements inside the retrieval algorithm, and we retrieve one single profile from UV and visible combination. And we increase this number of wavelengths. In previous version, we used only 3 UV pairs. Now we use 6 UV pairs and 1 triplet. We also now have a dynamical vertical range. So each pair is used only in places where it has the largest sensitivity. And then we implemented second-order Tikhonov regularization to smooth profiles, and we updated convergence criteria. And finally, we switch from gamma function aerosol, we switch from bimodal size distributions to gamma function distribution. So let's talk about this. So in order to retrieve ozone, we first need to get aerosol extinction. And we get aerosol extinction from 675 nanometer observations from the same instrument. But in order to retrieve aerosol, we need to assume particle size distribution. In previous version, we use bimodal particle size distribution. So essentially, when you correct for aerosol, you should expect residuals to be very close to zero. And with bimodal, which is a green line, we kind of saw consistent anomalies. Oh, I'm sorry. So when we switch to gamma function distribution, we see better results. It's a blue line. It's not completely zero, but it's much better than it was before. And this plot shows sort of like one orbit when we switch, when we only switch particle size distribution, and you can see where these changes will be, where it will affect ozone retrievals. Obviously, it's tropical UTLS, where ozone concentration is very small, so whatever you do with aerosol correction will always affect your ozone retrievals. And then it's northern hemisphere. And in northern hemisphere, it's because we have larger sensitivity to aerosol in northern hemisphere due to scattering angle. This plot kind of aims to show how we selected altitude ranges for each wavelength. So we try to keep consistent sensitivity across the entire range between 12 and 57 kilometers. And this is like bottom altitude for each wavelength in this table. So what we see as a result, this plot shows averaging kernels for version 2.5 and version 2.6. And in version 2.5, you can see switches where we switch from one UV pair to another. Now with Tikhonov regularization, we have much smoother transition, and we also have more wavelengths, so sensitivity never drops substantially when you switch from one channel to another. And then this plot shows vertical resolution and estimated precision. The vertical resolution is about the same, but as I said, because we have more wavelengths and we have Tikhonov regularization, it doesn't kind of, there is no oscillation in vertical resolution, which is blue line in version 2.6. The estimated precision decreased by a factor of 2, which is important because, for instance, for simulation purposes, the weight of measurement is proportional to, inversely proportional to its estimated precision. And our precision in version 2.5 was too large, so we kind of overestimated that precision. So finally, we report several quality flags in version 2.6 to make life of users easy. We report convergence criteria and number of iterations as a screening criteria, and it removes about 1% of profiles. Then we have flag, which is based on polar mesospheric clouds that can contaminate UV measurements at high altitudes. That flag illuminates very large amount, relatively large fraction of profiles, about like 4 to 4.5%. This is on NO based. Then wavelength shift. So essentially, our algorithm is designed to use specific wavelengths. If we don't have that wavelengths available in gridded product, we have a flag that kind of determines that. And then we look at final residuals. Our goal is to minimize differences between measured and calculated radiances. And that's why we always check final residuals. So this plot just shows you biases. I will only notice that because we combine now UV and visible, in version 2.5 we had very strong discontinuity when we switch between UV and visible, and now it's much smoother, but overall biases, the magnitude of the biases remains the same. So it's hard to say that this version is substantially improved biases. This is another look at this. This is plot from Sean Davis and Hugh Gia. They compared two versions. Version 2.5 UV and visible are shown as color lines, and the black line is for for version 2.6, and this is biases with respect to SAGE and MLS. So you can see that we have some improvement in that region where we merge UV and visible. I probably will skip this plot, so that's combination of LIMP and nadir, how we can derive tropospheric ozone. And I want to say a little bit about Honga Tonga eruption and how that affected our measurements. So this is a plot from Hassan with a stratospheric aerosol column. And as a result of this volcanic eruption, we have many events where our cloud detection algorithm detects a high amount of aerosol and triggers that cloud flag, so we don't have retrievals below. But even so, all retrievals that go through our quality flags are still kind of biased with respect to climatology, and you can see that there is more sort of variability in those retrievals. And this plot shows standard deviation for multiple years, which are shown as the red lines. And in 2023, we have larger standard deviation, which means that there are some anomalous measurements. And we also see changes in final residuals. So now we're developing a flag, and stay tuned, and we will update this flag. And another thing is that obviously aerosol affects our altitude registration. So now we have a lot of aerosol in Southern Hemisphere, and AirSAS method is not capable to handle so much aerosol. So we have substantial drop, which is obviously not a drop in altitude registration, but rather anomalies due to aerosol. I will stop on this slide, and if you're interested in getting our data, this is how you can get them. We report them at official NASA guest disk. We have Ozone IQ website. We also provide overpasses that are available on this website. And I want to say that near real-time OMS version 2.6 is available. Please contact us if you need near real-time product. Thank you for your attention.